Hey there, Kim fans, and welcome to our AP review of Topic 7.7, Calculating Equilibrium Concentrations, and also partial pressures. We're going to do two practice problems to help you remember how to use Rice tables in order to calculate equilibrium concentrations. There are a lot of steps and a lot of things to think about as you're calculating equilibrium concentrations, but the process is not too tough. You just need to really think about what you're doing, how initial concentrations are going to shift, and then how to do the math to calculate that shift. So we're going to do two practice problems. One where we're going to use equilibrium concentrations for gases, and one where we're going to use partial pressures for gases and the value of Kp. So let's go ahead and just dive in and remember how to do these calculations. So our first example here, we are given initial amounts of reactant, and there's no initial product in this reaction. So we have 0.05 moles of hydrogen reacting with 0.05 moles of bromine, both of which are placed in a 5-liter flask and heated to 700 Kelvin. And we're going to calculate the equilibrium concentration of all our reactants after we lose some of them, and our product after we gain some of it. So before we get started, we need to write the equilibrium expression for this reaction. Since we're dealing with concentrations, we're going to write the equilibrium expression for Kc, which means our product's concentration, which is HBr, raised to the power of its coefficient, which is 2. And then we're going to divide by the product of our reactants concentrations raised to their power. So H2 raised to the first power because it has a coefficient of 1 times the concentration of bromine raised to the first power because it has a coefficient of 1. So this is the equilibrium expression. So at equilibrium, the ratio between the products and reactants are going to equal our equilibrium constant, which is given to us 64 for 700 Kelvin. So how are we going to solve this problem? Well, we're going to use a Rice table. And I know some of you call it an ice table. I like to call it a Rice table because I like to put the reaction at the top to keep everything straight. So H2 plus Br2 yields 2HBr. Now, we are given the moles of the substance, but remember Kc is the equilibrium constant for concentration. So we actually need to find out the concentrations of our hydrogen and our bromine when they're placed in this 5-liter container rather than just plugging in moles. So we've got to first convert to concentration. And since we're given the same number of moles of hydrogen and the same number of moles of bromine, their concentrations are going to be identical to one another. So we only have to do this calculation once, which is nice. So we're going to take our moles, which is 0.050 moles, and we're going to divide it by the volume of the container, which is 5.0 liters. And when you do 0.05 divided by 5, you get 0.010 molar. So our concentration of H2 and Br2 initially, at the beginning of this reaction, is 0.01 molar. So that's what I'm going to plug in for my initial concentration of H2, 0.010 molar, and for Br2, 0.010 molar. What's the initial concentration of HBr? Well, you weren't given any HBr initially, and so its concentration initially is 0. So obviously this reaction is going to proceed to the right towards the products because all we have is reactant. So the reaction is going to proceed to the right. So we're going to lose each of our reactants, and we're going to lose X amount of hydrogen, and we're going to lose X amount of bromine because it's a 1-to-1 ratio. And then we're going to gain our product, and we're going to gain twice as much product as we lose of our reactant. So plus 2x. For equilibrium concentrations, we're just going to do the math. 0.010 molar minus x, 0.010 molar minus x, and 0 plus 2x is 2x. So these are our equilibrium concentrations. So we need to solve for x so that we can actually solve for what these concentrations are. So we're now going to plug these equilibrium concentrations with their x's into the equilibrium expression. So Kc is 64. The concentration of HBr is 2x, and that's going to be squared because we're plugging in the concentration, and that concentration is squared. We're going to divide that by the concentration of the hydrogen times the concentration of the bromine, 0.010 minus x. So now it's a matter of solving for x, and I am not mathematically going to solve for x here. But you do need to know how to solve algebraic equations to solve for x. And so in this particular problem, x is equal to 0.0080 molar is the value of x. So now we can solve for our equilibrium concentrations of each of our reactants and our product by plugging x in to the equilibrium expressions. So our equilibrium concentration for H2 is the same as our equilibrium concentration of Br2, and that is 0.010 molar minus 0.0080 molar. And when you do that, you get 0.0020 molar for the equilibrium concentration of our reactants. For our product, which is HBr, we're going to plug x in to its expression, which is 2x. So we're going to do 2 times x, 2 times 0.0080 molar. And when you do that, you get 0.016 molar. And that's our equilibrium concentration of HBr. And so that's using a Rice table to solve for the equilibrium concentrations of each of the species after the reaction has occurred. We are now going to do a problem where instead of using concentrations, we're going to use partial pressures because gases can exert pressure and equilibrium can be shown in terms of pressure. Remember, Kp can only be used for gases. So if there's any aqueous solutions or any solids or liquids, they would not go into your Kp expression. The problem we're going to use, every species is a gas, and so every species is going to go into our Kp expression. So in this example, we are given initial pressures for partial pressures for every single species in this reaction for both reactants and products. And our goal is to figure out what their equilibrium partial pressures will be. So the first thing I want to do is I want to write my Kp expression. So Kp is equal to the partial pressure of the products, so the pressure of NO raised to its exponent of its coefficient, which is 1, times the pressure of the other product, which is SO3, raised to its coefficient exponent, which is 1, divided by the partial pressure of sulfur dioxide raised to its exponent, and the partial pressure of NO2 raised to the exponent of its coefficient. So this is our equilibrium expression, our Kp expression for this reaction. Now we are going to solve this problem in a very similar way we did with the concentrations, but instead of using concentrations, we're going to use pressures. So we're going to make a Rice table. Our reaction is given right here, so I'm not going to rewrite it. Initial pressures, we're going to write those in. Then we're going to do our change in pressures, and then our equilibrium pressures. So our initial pressures, and we have to be careful because this is not written in order, SO2 is 0.150 atmospheres. The NO2, we look carefully in the problem, is 0.200 atmospheres. The NO, if you look at it, is 1.500 atmospheres. And sorry for that written in value. My original value was incorrect there, and so it's 1.500 atmospheres. And then SO3 was 2.000 atmospheres. And so these are the initial partial pressures of each of the substances. Now, one thing that's a little tough here is which way is this going to shift? Are the reactants going to make more products, or are the products going to shift and make more reactants? We don't know. We have to figure this out by using the reaction quotient. And so we're going to calculate the reaction quotient, which, remember, the reaction quotient is the exact same expression as the K expression, our equilibrium expression. But we're going to plug in our initial pressures to solve for the value of Q. And if Q is greater than Kp, then that means that we have too much product and we need to make more reactant. If our Q value is less than Kp, then that means we have too much reactant and we need to make more product. So let's go ahead and solve for our Q value here. So Q, we plug in all our initial pressures, 1.5, times 2.0 divided by 0.15 times 0.20. And when you solve for this Q value, you get a value of 100. Now notice we're given the Kp value in the problem. It's 85, and this Q value is 100. That means that our numerator in our Q expression is too great compared to what it will be at equilibrium. So our products are going to shift and make more reactant. So our product in the numerator here is going to shift and make more reactant, and that will bring this Q value down to our equilibrium constant value of 85. So whenever Q is greater than K, product makes reactant. If our Q value is less than K, then our reactant is going to shift and make more product. So in this case, we are going to shift to the left. We are going to lose some product. So we're going to lose X amount of product. And again, the coefficients are 1. So our coefficient in front of X is 1. And we're going to gain some reactant because the reaction is going to shift to the left because our Q value is greater than K. So to solve for equilibrium pressures, we simply do the math. 0.15 minus, plus X, 0.20 plus X, 1.5 minus X, and 2.0 minus X. So there's our equilibrium pressures. So to solve for X, we are going to plug into our equilibrium expression, our K expression. So we're going to plug the K value, which is 85.0. And then we're going to plug in our equilibrium pressures. 1.5 minus X times 2.0 minus X divided by 0.15 plus X and 0.20 plus X. Again, I am not going to go through all the math on solving for X, but you do need to be able to solve for X in this expression. Once you solve for X in this expression, you should get 0.013 atmospheres. And I would strongly encourage you to pause this video and make sure you can solve for X. So now we've got X, and that will allow us to solve for the equilibrium pressures, partial pressures for each of our substances by plugging X into each of our equilibrium pressures at the bottom here. So let's go ahead and do that. So our partial pressure of SO2 at equilibrium is going to be 0.15 atmospheres plus 0.013 atmospheres, which is our value of X. And so when you solve for this, you get 0.163 atmospheres. And so that's going to be the equilibrium partial pressure of SO2. We're going to do the same thing for the other three substances. The partial pressure of NO2, we are simply going to take our equilibrium concentration with the X and plug in for X. So that is 0.200 atmospheres plus 0.013 atmospheres. And when you solve that, you get 0.213 atmospheres. And that's the equilibrium partial pressure of nitrogen dioxide. When we solve for the equilibrium partial pressure of nitrogen monoxide, that's going to be 1.500 atmospheres minus our X value, so 0.013 atmospheres. And when you solve that, you should get 1.487 atmospheres. And then our last one, our partial pressure of sulfur trioxide, that's going to be 2.0 atmospheres, 0, minus 0.013 atmospheres, which is our value of X. And when you solve that, you should get 1.987 atmospheres. And so these are our equilibrium partial pressures. So the key in this one is, one, that you're using partial pressures, not concentrations. Since you're given an initial amount of every single species, you do have to figure out which direction equilibrium will shift. Will it shift to the right? Will our reactants make more products, or will our products make more reactants? And then solve the problem just like we did in the concentration example. Hopefully this was helpful and jogged your memory about how to solve equilibrium concentrations and pressures of each species. If you need have any questions or need any more help, of course, please ask me and I'd be happy to help you. Good luck with your studies. Bye-bye.